Welcome back to the next session of electrostatic potential and capacitance. Friends, with this we are almost completing the half of the chapter, that is electrostatics of conductors. So, related to the electrostatic charges, electrostatic field and electrostatic potential, how the conductor behaves. So that's such important 5 points are mentioned here. The first point says, inside a conductor, electric field is 0. Second point, at the surface of a charged conductor, electric field must be normal to the surface at every point. Third point says, the interior of a conductor can have no excess charge in the static situation. And the fourth point, electrostatic potential is constant throughout the volume of the conductor and has the same value as on its surface. Then fifth point says, the electric field at the surface of a charged conductor is vector E is equal to sigma by epsilon naught into n cap. And the sixth point says, electrostatic shielding. Let us discuss one by one. Inside a conductor, the electric field is 0. What is the meaning of this? As I said, so we can charge a neutral body in a 3-way: charging by induction, charging by conduction, and charging by friction. When this friction or the charging of a metal surface takes place, the charges are residing on the surface of the conductor, not inside the conductor. Suppose if there is a conductor inside, or if there is a charge inside the conductor, then it will influence the charges which are residing on the surface. As a result, the electrons or the charges which are residing on the surface will experience a electrostatic force due to the inside charge, hence they drift. But actually it is not possible, because in the static situation we don't have any charges inside the conductor. If there is no charge, there is no electric field. If there is no electric field, there is no potential. That is, if Q equal to 0, E equal to 0. If E equal to 0, V is equal to 0. Hence, inside the conductor, electric field is 0. Then, let's go to the second point. At the surface of a charged conductor, electric field must be normal to the surface at every point. They say here, if this is the body, at every point the electric field must be normal to the surface, always perpendicular to the surface. If it is not perpendicular to the surface, then what would happen? So let us discuss some more points which we have already discussed in the while deriving the derivation of electrostatic field due to at a point on the equatorial line of a dipole. So look at this. One electric field is going in one direction, another electric field is going in one direction. That means what? There are two electric fields moving in two different directions. Then what we did? We resolved the component. In the same way, if on the surface of a charged conductor, if the electric field is not normal, then we have to resolve the component, which must be parallel as well as perpendicular to the surface. One which is perpendicular will not affect anything, but one which is parallel, definitely it will affect the surface. As a result, the electrons will move. Then in this again and again I am stressing, this is electrostatics. That means what? Charges are at rest. Hence, again, this is not possible. Hence, at every point, the electric field must be normal to the surface. The interior of a conductor can have no excess charge in the static situation. We just see point number 1 and point number 3. Look at this. They are saying here, electric field is 0. If at what condition electric field is 0? When Q is equal to 0. Now read the point. The interior of a conductor can have no excess charge in the static situation. If they have any excess charge, let us say consider a volume. So in the volume, if I consider a conductor of area delta S or delta A, suppose in that situation, if charges are there, that charges are not enclosed by the surface. If that charges are not enclosed by the surface, obviously the electric flux is 0. Once the electric flux is 0, obviously we know that electric flux is equal to Q by epsilon naught. If electric flux is 0, obviously Q is also 0. Hence, the interior of the conductor can have no excess charge in the electrostatic potential is constant throughout the volume of the conductor and has the same value as on its surface. If we say here, inside the conductor there is no charge, excess charges. Inside the conductor electric field is zero. That means what? Even if we consider the electrostatic potential inside or outside the conductor or inside the conductor, there is no potential inside the conductor, hence no work is done. At what condition we say there is a potential? When we move a charge from one place to the another place against to the direction of the electric field. But electric field is zero according to point number 1 and point number 3. Point number 3. As a result, the electric field is zero. Though we move the charge from one place to another place inside the conductor, so potential will not vary because there is no work done. Hence, we can say electrostatic potential is constant throughout the volume. That's what the next point, that is the electric field at the surface of a charged conductor is equal to epsilon vector E is equal to sigma by epsilon naught into n vector n cap. So now friends, for this you just recall the applications of Gauss's law in that second application. What we said in the second application, so electric field due to a uniformly charged infinite thin plate sheet. For this we have calculated this expression. That means what? Every surface in the electrostatic field is considered as an uniformly charged thin plate sheet, and the expression for that is given by what? Vector E is equal to sigma by epsilon into n cap, where sigma is the surface charge density. And finally, electrostatic shielding. What exactly the meaning of electrostatic shielding? Let's understand some important concept related to this. Suppose if I take a volume like this, if this is the conductor, if this is a conductor, in this electric field lines are passing like this. Electric field lines are passing like this. So these are all electric field representing electric field line. Then what I will do? I will select a certain region in this conductor. Let's say one conductor space I will select like this. I will select this region. Look at this now. Electric field lines are passing but not crossing that area. Look at this. In this region, electric field lines are not moving or not crossing. That means what? E is equal to 0. If E equal to, at what condition E equal to 0? When Q equal to 0. If Q equal to 0, E equal to 0, obviously what? V is also equal to 0. That means what? I am protecting this conductor by shielding some space or the region inside the conductor. Then what is the electrostatic shielding? It is a phenomenon of protecting certain region of space inside the conductor. So now look at this. I have shielded this. So this is shielding. So I have shielded this region. So which is free from electric field, free from charge, as well as the free from the electrostatic potential. At what condition, in which situation we are preparing this electrostatic shielding? Friends, as 1 mark is concerned, this is very important definition. Define electrostatic shielding. Very simple definition. It is a protecting a certain region of space inside the conductor. So that's it. So now, at what condition we are using this phenomenon called as electrostatic shielding? So this is a phenomenon in which certain region of space is protected inside the conductor. So now we are using this phenomenon when we want to protect the highly sensitive electronic devices. So to protect such electronic devices from the effect of any electrical accidents or electrical hazards or electrical accidents, so electrical influences, to protect from the such thing, so we are using this process called as electrostatic shielding. Friends, with this we have completed half of the chapter. The remaining chapter will be continued in the next video. Thank you.